Hello, this is Jack Jackson, and we're back with a continuation of our series of videos on inferential statistics. In this video, we're going to start what might be arguably the most important part of an entire first course in probability and statistics, and that is the idea of a hypothesis test. This is a super big, important idea in statistics. So we're going to have a series of videos here working on this basic idea. And this is the first of this series on this. So actually there's going to be a series of probably 8 of these videos talking about what's called a one sample z-test, which is how we're going to introduce the idea of hypothesis testing. So this video is 4.4.1, Introduction to Hypothesis Testing, and we'll follow that up with a video showing you the test statistic method and the p-value method, and then a few examples, and then end with some calculator shortcuts at the end. So let's take a look at this introduction to hypothesis testing. So the basic idea behind hypothesis testing is to use information about a sample to infer what is happening about the population in general without testing the entire population. And this is the central idea behind inferential statistics. Hypothesis testing is what it does. It's used to determine the amount of difference between a statistic from an observed sample and either the corresponding assumed population parameter or perhaps a sample statistic from a different observed sample. And we're trying to decide if this difference is likely to be due to inherent randomness of the distribution or if it's more likely to be due to the observed sample being from a completely different distribution. Hypothesis tests are among the most powerful tools for making quantifiable data-driven decisions, which is really the whole point behind studying statistics. Now, this second bullet here is kind of a mouthful, and this will make a little bit more sense to you as we go along. So let's keep going with this. So suppose we find the mean of a sample and compare it to the mean of a known population. Now there's always variability, and even if the sample is representative of the population, the sample mean will likely be different from the mean of the known population. However, the sample mean will likely be somewhat close to the population mean if the distribution is drawn for them. Now, suppose the distribution of individuals is known in the known target population is normal. Even then, the sample means will vary naturally, and the distribution of those sample means should also be normal with the same mean and a smaller distribution than a smaller standard deviation than the distribution of individual values. So again, we know there's variation in almost everything. So we're looking at a situation where we suppose that there's a well-established history of some process with a known mean and standard deviation, and further suppose, at least for the moment, that the distribution of individual values is normal. When we find the mean of a sample, we would expect it to be close to, but not the same as, the historical mean of the population. Now, suppose that when we take a sample mean, it's not the same as the hypothesized population mean. It's off a little bit. Well, two things could be happening. It could be the difference is there because the normal variation among means of samples drawn for this population, or it could be that the difference is because the sample is really from a different population with a different distribution, a different mean. How can we decide which is likely the case? Answering this question is the main goal of hypothesis testing. So, these two different possibilities for the differences we describe as normal causes of variation and special causes of variation. So a normal cause of variation is a difference in means due to random variation in the distribution of sample means. The sample is from hypothesized target population, and this situation is likely if the differences in means is relatively small. And this is going to be the case that we assume is true unless there's a preponderance of evidence suggesting otherwise. The other possibility is that there's a special cause of variation. There's something special that's causing this variation besides just the normal distribution of sample means from a population. The difference in means in this case is due to something different about the sample. The sample is not from the hypothesized target population. This is likely going to be the case if the differences in means is large, sufficiently large. We will only assume this is the case if there is a preponderance of evidence suggesting that beyond a reasonable doubt, the special causes are actually present. So here are a couple of examples here. Normal causes of variation would be normal variations in weight changes from all people. People go up and down a little bit. If you've got a group of people and we would do their average, they won't necessarily be the same as the mean of a whole population. There's normal variation in blood pressure of all people. So if you do a sample mean, you will not get exactly the same thing every time. Normal variation in diameters of pistons from variations in materials, methods, and machines. Special causes of variation might be a large weight loss from a group of people that are on an effective diet. That would not be the normal situation. That would be something different. Large drops in blood pressure from people using effective blood pressure medicine. Or significantly smaller diameters of pistons from a broken or miscalibrated machine. Those would be special causes, and we would like to try to identify when those are happening. So hypothesis testing allows us to quantify what we mean by saying the differences in means, or perhaps some other statistic, is sufficiently large enough to have a preponderance of evidence suggesting that special causes of variation are present, and the sample comes from a different population than the hypothesized target population. So hypothesis testing allows us to put numbers to what we mean by sufficiently large and preponderance of evidence. It's going to give those, it's going to quantify what we mean by those terms. So basically, hypothesis tests allow us to answer the question, how do we determine if the sample data provides enough evidence to say that the sample mean is sufficiently different from what we would expect under normal causes of variation, so that we can conclude that the sample is from a different population? And if so, how can we quantify our level of certainty? That's the essential question that hypothesis tests ask. So what we basically do is assume that only normal causes of variation exist unless there is sufficiently strong evidence to suggest otherwise. So if we are trying to prove something, we typically assume the opposite until we have strong enough evidence to suggest otherwise. So the burden of proof is with the researcher. So this leads us to things that we call the null hypothesis and the alternative hypothesis. So we started hypothesis testing by establishing these things. The null hypothesis, usually labeled as H sub 0, pronounced H naught or H sub 0 or null hypothesis, is basically a status quo assumption that the distribution of sample statistics has some known distribution. In our first examples in the next several videos in this section, all of the ones in 4.4, we're going to be looking at several examples where the null hypothesis is that the distribution of sample means is normal with some specified mean that's known ahead of time and some standard deviation of the individual's sigma. The alternative hypothesis is what we're trying to prove, probably that the mean is something different than the hypothesized mean. Now, one of the best ways to describe what's going on is by way of an analogy. And we're going to use an analogy by comparing to the United States justice system. So remember that the most basic tenet of the U.S. justice system is that the defendant is presumed innocent until the prosecutor provides sufficient, overwhelming evidence to prove beyond a reasonable doubt that the defendant is guilty. Notice that the burden of proof is on the prosecution. The defense does not have to prove innocence. All the defense really has to do is to try to show that there's reasonable doubt. Okay, and so the bar is set pretty high here for the defense to provide this evidence. So this is the same thing that's going on in hypothesis testing. The null hypothesis is that the defendant is like the hypothesis that presumed innocence until proved otherwise. So the null hypothesis, H sub 0, is that the defendant is innocent and did not commit the crime. That may or may not be true, but that's the default, right? That's the status quo. We assume everyone is innocent unless we can prove that they're guilty. So notice that the defense does not have to prove innocence. They merely have to show that there is some reasonable doubt. It is up to the prosecutor, the researcher, to prove that there is evidence beyond a reasonable doubt that the null hypothesis is false and it's abandoned in favor of the alternative hypothesis. So the alternative hypothesis is usually labeled either H sub 1 or H sub A. Okay? And in the justice system, the alternative hypothesis is the defendant is guilty of committing the crime. So the prosecution has to show that the preponderance of evidence supports their alternative claim of guilt beyond a reasonable doubt. And again, the burden of proof is with the prosecution. So in general, the null hypothesis is the basic assumption that the sample came from some hypothesized target population with some known, say, mean. We assume that the null hypothesis is true unless there's very strong evidence to suggest otherwise. This assumption provides the probability statistics descriptions necessary to quantify the probability that the sample is from a hypothesized population. So this is going to describe the underlying distribution, like maybe a normal distribution, that we're going to use to perform our test. And the alternative hypothesis, on the other hand, is what we're trying to prove. So notice you basically assume that the opposite of what you're trying to prove is true, and that what you're trying to prove is false, and you have to provide enough evidence, the data has to provide enough evidence to show that there's enough evidence to reject the null hypothesis in favor of the alternative hypothesis. So notice in a justice system analogy, there are two verdicts. These correspond to the two conclusions that you can make in hypothesis testing. One verdict is guilty. That corresponds to the conclusion of rejecting the null hypothesis in favor of the alternative hypothesis. So in this case, the prosecution has provided enough evidence to convince the jury that the defendant has committed the crime beyond any reasonable doubt. Okay, and what that means, of course, in the hypothesis testing is that the data provided by the researcher provides enough evidence so that the null hypothesis is false and the alternative hypothesis is true beyond a reasonable doubt. And so what we do, we're going to be able to quantify what we mean by enough evidence and beyond a reasonable doubt. The other verdict that you could get in a courtroom is not guilty. And this corresponds to failing to reject the null hypothesis. In this case, the prosecution has failed to produce enough evidence to prove beyond a reasonable doubt that the defendant was guilty, so the default assumption of innocence prevails. Notice that there's a very subtle difference in a verdict of not guilty versus a verdict of innocent. They're basically the same thing, but there's a slight difference. The defense does not prove that the defendant is innocent. They merely fail. The prosecution just merely failed to prove that they were guilty. So it falls back to the default of presumed innocence. And so the prosecutor just failed to provide that evidence. And so that's the same thing in a hypothesis test. We never actually prove the null hypothesis. We just assume the null hypothesis if we don't have enough proof for the alternative hypothesis. Okay. Now, in a hypothesis test or a courtroom, there are two good outcomes, depending on what's the reality of the situation. A type A correct conclusion happens in the courtroom is when a verdict of guilty is determined and the defendant actually is guilty. Okay? So in general hypothesis testing, this corresponds to rejecting the null hypothesis in favor of the alternative hypothesis when the alternative hypothesis is actually true. So if the alternative hypothesis is true, and that's what you've said, you've made the correct thing, correct conclusion. So this is called a type A correct conclusion. The other type of correct conclusion you could make in the courtroom would be if the defendant is actually innocent, then the correct outcome would be a verdict of not guilty. So, for example, if you watch Perry Mason or Matlock or some of these shows where it's centered on a defense attorney, this is what always happens, is they get a verdict of not guilty, and they're able to cast enough reasonable doubt usually by getting somebody else to confess in that case. But anyway, they get a verdict of not guilty. Type A correct conclusion is going to be more of a show where they catch the bad guy and try him, and you're on the side of the defense attorney. Not the defense attorney, but the prosecutor in type A correct conclusion. So in general, in type B correct conclusion, in general hypothesis testing, this is failing to reject the null hypothesis when the null hypothesis is actually true. That is what you want to have happen if the null hypothesis is actually true. You don't want to reject it, and so that's a type B correct conclusion. But just as there are two good outcomes, there are two bad outcomes. If the defendant is actually innocent and the outcome of the trial is guilty, then the jury made an error. They're sending an innocent person to jail or punishing them. So in general hypothesis testing, this is when we reject the null hypothesis in favor of the alternative hypothesis when in fact the null hypothesis was actually true all along. This type of error is called a type 1 error. The other type of error could occur when the verdict of the trial is not guilty, but the defendant is actually guilty of the crime. In general hypothesis testing, this is when the null hypothesis is not rejected, but the alternative hypothesis is actually true. So maybe some evidence was presented that they were guilty, but not enough to convince the jury. That wasn't beyond a reasonable doubt. It was not sufficient evidence. And so in that case, you make an error, but it's called a type 2 error. Now, do these things actually happen? Sure they do. There are examples where guilty people are set free and given a verdict of not guilty. And there are certainly cases where innocent people are convicted as well. So both of these type errors happen both in the justice system. Hopefully not very often in either case, but they do happen, and they do happen when you're dealing with hypothesis testing. Okay? Now let's examine this a little bit more. If we reject the null hypothesis in favor of the alternative hypothesis, then we can only have made a type A correct conclusion or a type 1 error. Okay? Those are the two things that could happen if we reject the null hypothesis. If we reject the null hypothesis, there's no way we could have made a type B correct conclusion or a type 2 error. Likewise, if we fail to reject the null hypothesis in favor of the alternative hypothesis, then we could only have made a type B correct conclusion or a type 2 error, depending on what happened in reality. But there's no way you could have made a type 1 error or a type A correct conclusion in that case. However, in reality, either the null hypothesis is true or it's false. The defendant's either guilty or innocent in reality. So if the null hypothesis is actually true, then we either made a type B correct conclusion if we fail to reject the null hypothesis, or we make a type 1 error if we rejected the null hypothesis in favor of the alternative hypothesis. So those are the two things that could happen if the null hypothesis is actually true, like the defendant is actually innocent. On the other hand, if the null hypothesis is actually false, right, then we've either made a type A correct conclusion if we reject the null hypothesis, or we make a type 2 error if we fail to reject the null hypothesis. So if in reality, either the null hypothesis is true or false. If it's true, we had to make a type B correct conclusion or a type 1 error. Or if the null hypothesis is actually false, we made a type A correct conclusion or a type 2 error. there are actually conditional probabilities associated with each of these four outcomes. So, first of all, a probability of type 1 error we call alpha, and it's the probability that reject the null hypothesis given that the null hypothesis is actually true. We call that alpha. Notice that this is the probability of a type 1 error. It is a conditional probability, and we call its value alpha. The probability of a type B correct conclusion is the complementary probability, 1 minus alpha. It's also a conditional probability, and the condition we know for a type 1 error and a type B correct conclusion, okay, is that the null hypothesis is actually true. Okay? So the type B probability of a type B correct conclusion is 1 minus alpha. It's the probability that we fail to reject the null hypothesis given that the null hypothesis is actually true. Notice that's also a conditional probability. Notice that if the null hypothesis is actually true, the only possible outcomes are type 1 error or type B correct conclusion. So these are complementary probabilities. They add up to 1. So the probability of type B correct conclusion is 1 minus alpha. Now, on the other hand, if we look at the conditional probabilities where we're given that the alternative hypothesis is true, so the null hypothesis is false. So the probability of a type 2 error is beta, and it is the probability, it's a conditional probability. It's the probability that we fail to reject the null hypothesis given that the alternative hypothesis is true. Its complementary probability, 1 minus beta, is the probability of a type A correct conclusion, and that's the probability that we reject the null hypothesis in favor of the alternative hypothesis given that the alternative hypothesis is actually true. So the probability of a type A correct conclusion is 1 minus beta. This value, 1 minus beta, is also known as the power of the test. So here's a table that kind of summarizes this. The four outcomes. We either have in this column that the null hypothesis is true, the defendant is actually guilty, the defendant is actually innocent, excuse me. That's the null hypothesis, the default assumption. And either we get a type 1 error, innocent defendant is convicted, or a type B correct conclusion, innocent defendant is acquitted. Over here in this column, we have the alternative hypothesis is true. That's either a type, in other words, the defendant is actually guilty. So this is a type A correct conclusion, a guilty defendant is convicted, or a type 2 error, a guilty defendant is acquitted. This line here is that we reject the null hypothesis in favor of the alternative hypothesis. A verdict of guilty is returned, and that means we either made a type 1 error, we convicted an innocent, or type A correct conclusion, we convicted a guilty person. And the bottom line is we failed to reject the null hypothesis. For example, a verdict of not guilty, that's a type B correct conclusion, like an innocent is acquitted, or a type 2 error, a guilty person is acquitted. And then here's a table of the four conditional probabilities. Alpha in the upper left-hand corner is the probability of type 1 error. That's the probability to reject the null hypothesis given the null hypothesis is true. The corresponding thing with the justice system is the probability that the defendant is convicted given that he's innocent. The complementary probabilities right below that of a type B correct conclusion, that's the probability that we fail to reject the null hypothesis given the null hypothesis is true. That's the probability the defendant is acquitted given that the defendant is innocent. And then over here we have 1 minus beta is the probability of a type A correct conclusion. Probability to reject the null hypothesis given that it's false. That's the defendant is convicted given the defendant is guilty in the justice system analogy. Probability beta is the probability of a type 2 error. We fail to reject the null hypothesis given the null hypothesis is false. So the probability the defendant is acquitted given that the defendant is guilty. Now, notice we have these two errors, type 1 error and type 2 error, and their probabilities alpha and beta. Well, these are errors, so we want the probabilities to be very small. We want both alpha and beta to be extremely small. The only problem is, do you see that they work against each other? So, ideally we want alpha and beta to both be very small, but usually making one of them small makes the other larger. For example, decreasing the chance of convicting an innocent person, smaller alpha, will likely increase the chance of letting a guilty person go free, larger beta, and vice versa. So which is more important, alpha or beta? Well, whether you agree with it or not, many people will say in the American justice system, a basic premise is it's better to let a guilty person go free than it is to convict an innocent person. So more attention is placed on making alpha small. You may or may not agree with that premise, but that's kind of a way it's set up, and it's certainly the way it's set up in hypothesis testing. So in hypothesis testing, we're mainly concerned about controlling the size of alpha. Sometimes we're looking at beta or 1 minus beta as well, but we're mainly designed the entire test around making alpha small. So what we do is we actually decide on some acceptable level for alpha, and then we use our knowledge of sampling distributions to determine a threshold beyond which we have sufficient evidence to reject the null hypothesis in favor of the alternative hypothesis. So note that alpha can be any small value, but it's very typical to choose either 0.1, 0.05, or 0.01 for alpha. There's nothing really sacred about those values. It could be anything else, but they're kind of the ones that are typically chosen, the usual suspects there. So the choice is made based on how comfortable we are with making a type 1 error, because it is, after all, the probability of making a type 1 error. And the appropriate choice for alpha may depend on the context. So, for example, in a manufacturing context, we might be okay with a larger alpha, like alpha's 0.1, or maybe even we might be comfortable with something even smaller than that, or larger than that. Whereas in a drug test, we're very uncomfortable with making a type 1 error. So we may want a smaller alpha, like maybe 0.01. Okay, so that concludes this video showing us the basic idea of a hypothesis testing and setting up what we mean by some of the basic setups. In the next video, we'll actually talk about how to actually compute a hypothesis test, a z-test, using the test statistic method.